All right, everyone. This is this is our last formal lecture. Next week is sort of wrap up kind of administrative things that we'll talk about. So this is the last sort of lecture. So presentations are starting tomorrow. Looks like we got a number of people. Looks we got some filled up. Okay. I'm going to send an email shortly. Unfortunately, the people who need to hear this probably aren't here or are probably not watching the recording. But just in case, if you're one of the few that have not signed up for your presentation slot yet, you're probably going to get an email from me, and hopefully you're watching this because of that. You should reach out ASAP so we can figure something out. If you could message, if at this stage, email Angela and I together. If you haven't signed up and you need to present, the semester ends next week, so this is really home stretch. So please do that as soon as you can. I am going to be on the train for a lot tomorrow, and I'm worried about snowstorm, so we'll see how that works out. But I might be delayed in responding, but I'm going to try to stay on top of email tomorrow. Paul is asking, can we since it's mine and it's a Thursday, and I'm going to be doing it from a hotel. Yes, I put it number 10. Put your name in, Paula, right now if you can. Uh, um, so yeah, that'd be fine for that one. Um, Anything else to say about this at this stage? Any questions about like where we are on the semester? So yeah, we'll do a little wrap up next week. Talk
Quick
about some.
question. I just wanted to ask, is that data going to be available I mean, there is so much really great resources that you have on your page over there. Is that going to be still accessible after the semester ends?
Yeah. I'll go through it next week and as well because I have some slides on it. But so the short answer is yes. Just be careful. I don't know. I always just when I want to go to it, I just type data606.net and it does a redirect. So sometime in early January, it'll start to redirect to spring 2026. But as long as you type in this fall 2025.data606.net as the URL, you will get to this. The other thing I will point out next week is this little hit link here. And if you ever notice at the bottom of each page, there's like this edit page. So if I click that little GitHub icon, the whole website is actually hosted using GitHub Pages. If I go into settings, pages, um, it's all in GitHub Pages. But you can come in here and you can either clone this or download a zip file. But I would recommend to wait until like after next week because I'll still be adding a little bit of content next week. So if you download it now, you'll just miss the last bits of things. But yeah, you can certainly download the entire repository. So the website is in this website folder. There's all the course data. There's R scripts. Some things you could see some old data. Anytime I do R scripts, I often just save them in here. Sometimes it's date, sometimes. So there might be even things in here that because they're just remnants from past semesters, you could always browse through. But yeah, everything's here. Um, yeah. So yeah,
Awesome.
yeah,
Thank you.
yep. Um, well, we'd be meeting using this. I just want to. Oh yeah, use this meetup. Yes, good question. Use for the meet presentations. Just use the same link as the Zoom meetings. Angela, you are a co-host, right? I think so. Yeah, because you always come in. Right. Great. I
Yes,
just want to
yes,
make
I do.
sure you can join if I'm not there. I get it
Yep.
started. Um, so good question, Zoran. Um, so we'll have an opportunity. So just another quick announcement. There is a final exam. It'll be available next Monday. It will be due the following Sunday. So you have basically 1 week, a few hours less than 1 week technically, but essentially 7 days. So that'll just be on Brightspace. So you have to go there to get it. That's not on the course website.
Sorry to interrupt. So the final exam, is it a cumulative or is it just for the material after the midterm?
Uh, Mostly after.
Okay.
mostly after. There may be a question or two in the multiple choice that harkens back to the first half, but I don't think maybe one or two. But the bigger chunks, the bigger portions of it is all stuff from the last few weeks, in fact. But I think a lot of this builds. So in order to interpret it, some stuff you're going to need to know what came before it. But just as a reminder, I think I've said this before, but it's worth repeating. I think there's 10 multiple choice questions and a toy data set. So the way it'll work is there'll be a PDF that will be sort of the exam with the exam questions, and then there'll be an R Markdown file that you'll download as like your answer sheet, if you will. For the multiple choice, you'll see there's a bulleted list that 1 through 10. You can just put A, B, C, D next to it. And then for the small data set, the data set's actually embedded in the R Markdown file. So you're going to see this giant chunk. Well, it's not really that giant, but it's, all the numbers are kind of inline. It's just, and so you once you run that chunk, your data set will be there. So you don't have to load anything. It's just going to run that chunk and it's there. And then you're going to it's going to ask you to do a bunch of stuff. And then there's some interpretation questions at the end based on the analysis you did. So think of it as like the on your own section of, without the scaffolding before it. So we're not out to trick you. It's not, you can use your books, use your textbooks. I would not, I think, although maybe you can tell me anonymously later, I think ChatGPT and the similar will not do well with these questions, at least with the second part. I suspect, but I could be wrong because they're getting really good. All right, so I wanted to kind of quickly cover two things. Like, so tonight is not on the final exam, but hopefully I want to kind of revisit something we talked about way back at the beginning. And we talked about there are sort of two broad views of interpreting probability, right? And really, most of this course, or until now, really all of this course has been from the frequentist point of view. And the frequentist point of view, right, is really predicated on this notion that there's something that exists called a sampling distribution. Like if we could take an infinite number of random samples, we could figure out what the real parameters of some population is, right? That's kind of in a nutshell what's going on, right? So we have one, and so if we know the sampling distribution is going to approximate the normal distribution, we know the properties of a normal distribution. We kind of say, well, we think the center's here. The standard error, which is the standard deviation of that sampling distribution, et cetera, et cetera. Okay. And that goes all the way up through regression. Like we're kind of leveraging that way of making inferences. But there's another approach, a Bayesian approach, and it's been around for actually quite a while. I think the first no, did not mean to do that. I don't know what that is. Okay. Let me see if I have it here. Oh, I don't. Okay. It'll come up in a little bit. I think the first paper written by Bayes is in the late 1800s, right? And it's come and gone a lot. So I'm actually starting with the resources up front. A lot of times I say, oh, if you want to learn more, if you really want to learn this, I'm only giving you a taste and to give you a sense of, and also to kind of contrast it to the frequentist approach, hopefully to reinforce what the frequentists are saying and seeing how the Bayesians do it a little bit differently. As an aside, I've been having a back and forth with my colleague at the University of Albany, whose name you see, I've used some of his apps. And so you may see an article from me soon in terms of, I may put it on my blog. So if you follow the blog or if you follow me on Mastodon, because I'm really starting to find myself, I may fully become a Bayesian in the next year. I've sort of dip my toe in either place. But there's this notion of infinite samples that is really bugging me a lot as I dig into some nuance and some things that we're doing. So I've been working on an article to kind of explore this notion of infinite versus finite populations and what implications it has for the standard error. I don't want to really go down that path. Maybe at the end, if somebody's interested, I could kind of show the working code that I'm using to simulate some of this stuff. But I use bootstrapping all the time, and that's one of my go-tos because I like that I can just simulate a bunch of data. And that's often what Bayesians are doing too. We're going to see it didn't really catch on in academia until like the 1980s, late 1980s, early 1990s. In part because I think high-speed computers started to become readily available. You could have a computer on your actual desk, right? That was sort of a new phenomenon. We're going to see that's going to be really required for this to work. But if you're interested in the history of Bayesian analysis, this uh, where is it? The theory that would not die is a fantastic. It's more of a history book, but it's like the history of Bayesian. So it's they have some pretty good descriptions of Bayes' theorem and the like, and how it works. But it's really about the history, and it, he goes back to Bayes, but a lot of you probably know the most famous Bayesian is Alan Turing, right? A lot of people know the Turing test, especially now with the advent of AI, right? This is kind of a major thing. But he became most famous because he created the Enigma machine that actually broke the German encryption codes in World War II. And he couple of things. He used large computers, but he also used Bayesian principles in order to do that, because we're going to see with Bayesian, we're not going to start from scratch. We could start with some kind of prior information, incorporate that into our models instead of always oriented towards the null. There are some other things where it's been used to search for, at post World War II, there were some sunken missiles, nuclear missiles at the bottom of the ocean, and how do you search for that and using search grids, and you can update and a whole bunch of stuff. So, um, Krusky, this is sort of my go-to book. Krusky's doing Bayesian data analysis. I think it's fairly accessible. That gives a pretty nice introduction. It's a pretty thick book, but there's a lot of stuff. And I have a link to his YouTube channel, and he has a bunch of YouTube videos up there. And I would also, so what I'm going to talk about, I'm actually stealing some content from Rasmus Bath, who really helped me fully understand it many years ago now. But he also has a three-part video series that I think that introduces it really, really nicely. So I kind of eschewed this. This I think is in the textbook, Bayes' theorem a little bit in the probability chapter, but Bayes' theorem is written like this, right? So we're talking about probability of A given B, like so probability of some event when you know something else. And this is kind of complicated, but in a probability sense, it's really useful in these kinds of contexts. And I think talking through an example makes the most sense. So let's say we want to know, let's just say we have the following data about breast cancer data, both from test and having possibility. So from prior research, this is a bit dated now. About 1% of women have breast cancer. So then the complement, right? So the probability of A is 1%. The probability of A complement would be 99%, right? Okay. We know mammograms detect about 80% of breast cancers, and then since therefore 20 miss. And 9.6 of mammograms detect breast cancer when it's not there. And so therefore 90.4 return a correct negative result, right? And so we could put this in this 2 by 2 table. But unlike other 2 by 2 tables we've had before, the columns add up to 100, not all the cells, right? So, when we want to ask the question, how accurate is a test, right? What we really need to know is, well, if you got a positive test, right? So we want to know, so if you get a positive test, what's the chances you actually have cancer? So we want the probability of cancer given a positive result, right? And so we can use Bayesian formula, and so that would work out to be so the chances of a true positive is about 1%, or I'm sorry, 0.8%, but the chances of a false positive, right? So if you got it, is like I guess that's 9.5%. So when we think about how accurate a test is, right, it's the probability of the desired events against all probability. So if you got a positive result, there's still only a 7.8% chance you actually have cancer, right? And we get through this through Bayes' theorem, which allows us to get the probability of some event given something else through other components. Okay, so Bayes' formula through some we can actually simplify it down to this. from a modeling perspective, right? Or what are the components, right? So from a modeling perspective, what we're often going to be left with is like Bayesians are going to view the data we have observed or collected as the truth. And so what we essentially we want to know is what's the probability of some outcome given the data we've observed? Okay. So we break these into different parts. So the posterior is the outcome we want. So from a Bayesian perspective, the posterior is where we're going to get something like called a credible interval, right? Which is sort of the analogous to the confidence interval, right? We want to say we observe something. We know it's probably not precisely correct, but the true answer is in some interval, right? That's essentially what a confidence interval is trying to do. But we get to the confidence interval through this notion of the sampling distribution, which we really never observe, but principles and theorems have been shown that holds. We're going to get that from some likelihood. Okay. So we have to define what that is in a minute. Some prior, right? So baseline information. And we'll see the prior could be naive, meaning we could assume nothing, or we could specify and say, well, prior research says this. Let me, include that. And then we're going to have the marginal likelihood. So for me, it's a little bit easier to understand this through an example. And I like this example because this is a problem that is really hard to solve using frequentist approaches. In fact, I'm not sure you really could without collecting more data. So this is like an estimation problem. We want to know how many fish are in a pond. Okay. And so what are the couple things we do? We could try to catch all the fish, but that's certainly not practical or even possible. Okay. So we have to have some kind of sampling scheme. And so what I propose is I'm going to go into this little pond. I'm going to go out in my little boat and I'm going to catch 20 fish. Okay. I'm going to put a little tag on them. I'm going to mark them. I'm going to put them back in the pond and wait long enough that they could shuffle, right? I need them to swim around so they could be anywhere in the pond. I'm going to go back out on my boat and I'm going to catch 20 fish again. And I'm going to count how many fish I caught a second time. How many were marked, meaning I caught them both the first and the second time. And let's say for argument's sake, I do this and I go out and on that second catching, that second time I caught 20 fish, 5 were marked, meaning they were caught 2 times. With only this information, I want to be able to estimate how many fish are in the pond. Okay. So I know nothing about estimating populations of fish in a pond, so I'm going to use what's called a uniform prior. And essentially you can think of the prior as my guess, right? And so here I'm using a uniform, so I'm doing 100,000, and so I'm sampling. There has to be at least 20 because I caught 20 fish, and I have to put a ceiling on this somewhere, right, for a uniform. And I'm going to say, well, it's a pretty small pond. I can't imagine there being more than 250 fish. So I'm going to say it's 250 is the cap. I could be wrong and maybe I should go higher, but and so here you could see I'm just calling samples. So I'm going to say I'm going to guess there's 205 fish in the pond and then 150, 174, et cetera, et cetera. And I got 100,000 of these. And this is what the prior distribution looks like. The next step is I have to define a generative function. Okay. And this is, in essence, I'm just replicating my strategy. So I'm going to create a function called pickfish, and I'm going to pass in a parameter which is my guess of how many fish are in the pond. So what am I going to do? So first thing, I'm creating a vector where I'm going to repeat 0. Well, let me go backwards. I'm going to repeat 1 20 times, and then whatever my guess minus 20 is 0. Okay, so what does that mean? So if I'm going to guess there's 100 fish in the pond, I'm going to have a vector of 80 zeros and 20 ones. This is essentially doing that. I caught 20 fish and I marked 20 of them. And then the rest are not marked. That's what this bit is. The fish I didn't catch are not marked. And then I have 20 marked. Then I'm just going to sample 20 fish from this vector, right? I'm going to and add them up. Right? So if I select a 1, that adds 1, and otherwise it's 0. Okay, so let's So here I'm going to initialize a vector called n marked, and I'm initializing it with missing value. And I'm going to do this, I think, 100,000 times. And I'm just going to loop through. I'm just calling pick fish. So in essence, what I'm doing is say, well, let me call this function. And I'm going to say, I think there's 250 fish. Okay. Calling my function, I got 4 marked on the second one. When I called with 115, I got 3. When I called with 174, I got 3. When I called with 24, I got 17, right? It's smaller. So does this make sense? So there's actually a relationship here, right? The bigger the number. But what I want to do here now is I'm only going to keep the ones where the number of marked equals 5. Why? Because that's what I saw when I went out on my boat, right? And so here I can plot this. This is called my posterior distribution. This is the distribution of the number of fish in the pond that meet the criteria of what I actually saw. Okay, so the median is somewhere around 100. Now, note this distribution skewed. Bayesians don't have any assumptions of normality here, right? That doesn't matter, right? The distribution is the distribution. And so I could define a credible interval as like, I just want to, the 50%. And so that's what I did here is I took I did a 50% credible interval, which says I'm 50% sure there's somewhere around like 75 and like 140 fish in the pond, right? So that would be my guess. But this distribution tells me, the likelihood, right? There could be 50, but it's less likely. There could be 250, but that's extremely unlikely, right? So I can look at the mean, where the sort of the center and mean may not be the best, which is why I used median here because it's skewed. I want to be more towards the middle. So we have a prior, we have posterior. So that prior doesn't have to be uniform. It doesn't. I used the uniform, which might be considered a naive because I didn't know anything. But let's say I go to the pond and there's some old fisherman here that says, I've been fishing this pond for, 60 years. I think there's 200 fish in this pond. I'm an expert. Okay. So great, right? I should leverage that information. So instead of defining my prior as a uniform, I'm going to say, well, let me use I'm going to draw from the binomial distribution, right? Centered on 200. I minus 20 because the binomial is bounded at 0, so I got to kind of account for that. And you'll see I'll add the 20 back later. Oh, it's right here. I add the 20 here. So here's the distribution of my guesses, right? So I'm going to guess around 200 more than any other value, right? And as I go out, so in this case, I'm actually going to make guesses over 800 fish in the pond, right? Even though I, might not be there, right? So this is my prior. The rest is the same. I'm just repeating. This is the same as the, a couple of slides ago. The only difference now is this n fish, right? Is not from a uniform prior distribution. It's from a binomial prior distribution. And here's my posterior distribution. I like to show this, right? So my median is a little higher, right? 120. But my 50% credible interval still captures 100, which is what I got from the uniform, right? So what I'm trying to say here. So one of the criticisms of Bayesian analysis is you could potentially specify a prior that may bias, right? People generally don't do that. But then also, these methods tend to be fairly robust to, even moderately bad prior distributions. So in this case, I like this 200 because that's clearly a bad prior. There can't be 200 fish in this pond. But even if I use this as my prior, my posterior still captures probably closer to where it really is. Okay, so am I calculating the time to catch fish as well? I'm assuming no fish die or born in that gap between my first and second catch, right? So there's some other assumptions, but I'm not accounting for that here. I'm just assuming it could almost happen simultaneously. All right, so the next thing I want to talk a little bit, because I love this example, and I built a Shiny app to kind of look at it. So Bayes' first paper was on this. He invented this game using a pool table. That's what statisticians did 100 years ago. They invented these crazy games, or they just tried to understand casino games. Right? That's what like early statistics was about, it seems. And so what Bayes proposes, say, I have a pool table, and let's just say it has a length 1. Okay. What I'm going to do is I'm going to throw an 8 ball, and it could be anywhere on the pool table. Let's presume I throw it so it could land anywhere on the pool table with equal probability. I'm not going to tell you where the 8 ball is. What I'm going to do is throw another ball, and all I'm going to tell you is whether it landed to the left of the 8 ball or to the right of the 8 ball. And with that information, you have to tell me where the 8 ball is. Right. So this is like 1890 something. Bayesian, proposed this. So I created a little shiny. Okay, so here we go. So the 8 ball, we could see I have a little checkbox. We're not going to cheat, but this we'll be able to see where the 8 ball really is. And so after the first, I learned that the 8 ball, I'm sorry, the ball I threw landed to the left of the 8 ball. So that's one throw. So what am I going to do here? So I'm going to start with the uniform prior. Ignore that there's this flare off. That's an artifact of how R does its density calculations. It is truly flat. Oh, in fact, I think here I can look at histograms instead, so you can kind of see it doesn't really flare off at the end. I'm coming in. I have no idea where the 8 ball is on the table. I know nothing. But I'm going to say, okay, these are all my guesses. And my generative function, which I was in the About tab, but I don't know why it's not showing up, right? What I'm going to do is draw a random number between 0 and 1. If that number is less than my input, right? Meaning it means it's to the left, right? I'm going to keep that. Otherwise, I'm going to throw it away. So I'm just simulating throwing an 8 ball using all of these guesses, and I think I have like 5 or 10,000 here, right? And I'm going to keep all the situations where I got what I want. And this is now my new guess, right? So hopefully intuitively, if I told you the ball landed to the left of the 8 ball, the likelihood of the 8 ball being on the right side of the table is much higher than on the left side, just given that one bit of information. And if I look at that distribution, the median is this black dot, and I have a 50% confidence range or confidence interval, which you can adjust here if you want it to be bigger. All right, great. Let me throw another ball. This also landed to the left. Okay. But now I'm not starting from scratch. I'm going to take the posterior distribution from my first iteration and make that my prior in the second one. And then I just run that generative function. So after 2, I'm going to shift my guess a little bit further to the right. I think the 8 ball is a little bit more to the right. Right. I could do another one. Oh, also to the left. So I took that posterior, it becomes the prior on this one, and I rerun. I can do another. To the left again. To the left again. Oh, now I got one to the right. Okay. So we took the posterior here, becomes the prior here. Now it landed to the left. And I got a right. So you could see it didn't go all the way to the right, right? It's just jumped a little bit to the left, right? And I could do this a few more times. Another right. So you could see it bounced back a little bit. And so now I've just done 8 iterations. I got 8 observations, right? And let's see, where's the 8 ball? There it is. Oh, we were doing good, and then we jumped left a little bit. So we kind of missed it from our 50% at the end, but we're in the ballpark, right? And so you can see I have labeled up here where each of the iterations from this table line up. So that's what Bayesians are doing, right? They're going to say, I have some data. Let me generate or simulate data and see what I actually have, right? So this is, I think, a big contrast from the frequentists. The frequentists are always oriented to the null. We're always, whether it's null, literally null hypothesis testing, but even in a regression context, right? We're still kind of working from the notion that the residuals are null and kind of moving off that to see if there's actual a relationship there. So Samuel asks, is Bayesian analysis more useful than classical hypothesis testing? Um, I don't know if it's more useful. This is an interesting question. And at the outset, I said I've been for the last few years and in the last couple of weeks struggling with some bits of frequentist analysis. I don't. I think they both have their place. Now, I live in a world like doing educational and social research where hypothesis testing is still used quite a lot. Even in the data science world, Google made A/B testing really popular and famous. And when they analyze that, they're still probably using frequentist null hypothesis testing and p-values and confidence intervals. Um, what you'll find when you get in some of the more advanced courses, there will be sort of Bayesian logistic regression or like analogs to logistic regression, but using Bayesian approaches. So the way the parameters are estimated is going to be this notion, right? I have some data and it's just going to try to estimate where those parameters give the data by simulating other data. And what I'm finding in practice in terms of predictive modeling, like I still think random forest, which I didn't really talk about, random forest is still one of the more accurate and useful predictive models, but sort of right behind that is Bayesian additive regression trees, BART. So if you look that up, and you'll learn that, I think in 622 or 624, I'm not sure
Isn't
where.
it slower too, though? The random forest
Well, they're both
because of the tree.
computationally intensive in terms of training, so that's another reason why you might want to avoid it. But was there more to your question? I'm sorry, it came in kind of loud.
I'm sorry. No, no, no. No, it's just I didn't want you to jump to another subject and then
Oh, no, no, no.
it'd
No,
be
do you have
irrelevant
other?
after that.
No, I'm about to jump to another topic. So why don't you ask your Bayesian questions?
No, no, no. That's all I had about the random forest. It was regarding the random forest. You mentioned random forest, and I
Yeah, yeah, it
remember that
is.
it's a little slower, especially like when you're using it in an R.
Well, the R implementation actually, I think, calls Fortran under the covers. So I think it's actually implemented in Fortran, even though it's in R. But yeah, random forest by virtue of you're growing lots of random trees takes more time to train. But here's my do we need oh look at that auto solve. I'll throw a link to this paper in. I'm a big fan of this paper as a practitioner because it kind of they so what did they evaluated 179 classifier models across 121 data sets. And the classifier to be among the best is random forest, right? So that's a lot. Angela and I worked with some students about a year and a half ago. Is that right? Someday I will revisit this. We started working on a package called ML Dash, where we were trying to update it. Why is that not pasting? I'm getting there we go. So if you're interested in this, so I guess it's been 2 years. So this is an R package, but we tried to create a framework to evaluate not just classification problems, but also regression problems and time series. I think we had some time series models. And I'm trying to remember, I looked at this recently. We only have currently 45 data sets, but we have 417 models. So we have more models, but fewer data sets. And the way this works, if anybody's interested, this could be an interesting side project if you're um, is the models and data sets are defined in these DCF this kind of data structure file. And so these are, you could pull the data. So we're pulling a lot of data from the UCI. There's a lot of data from Kaggle, from different sources. So if you want to add a new one, you don't need to write R code. You just write this kind of properties file and it'll bring it in. And it's similar for models, which is, I think, is kind of what made this clever. So we kind of define a naming convention. So using the carrot package, we're using, I don't even know how this one works. ANFIS, if anybody knows, you can chime in. Additive network based fuzzy inference system. There are a lot of, whatever. So you do this, so you have to write a little bit of R code, but a lot of these are free because the carrot and then what's new here is some are through the carrot package. The TM stands for tidy models. Then we even have Weka, which is a Java-based predictive modeling framework. So anyways, if anybody's interested, but we found similar results, random forest. We were interested because that paper didn't have XGBoost. It hadn't come out yet. That paper hadn't been published before they did that paper. So, and that's another popular one. Anyways, BART methods. There is another. Oh, I'm going to talk about it a little bit. So we have about 15 minutes. I'm going to do a kind of fly through this just again, also to kind of do contrast to what we did this semester. I like to say we did statistics or data science for inference this semester, which I think is important because hopefully you got some, hopefully I explained well some of the underpinnings, the assumptions, and the workings of how these models are trained. But I always presented it in the context of we're really trying to describe the relationship between variables. Now, in data science, we often train models for prediction. So our point of view and orientation and how we check models is going to be a little bit different. So a lot of times when we're doing just for prediction, we might not care so much about multicollinearity, only insofar as it may have an impact on our predictions. Okay. And so here, right, so this is going back to the logistic regression where we have the whether or not you passed an exam, and we could get predictions. This is nothing new in terms of getting predicted probabilities. Similar for regression, or we could, fitted values as we go through. But the way we generally evaluate, particularly classification problems where we have a 0, 1, is going to be, this is going to look, hopefully this looks a little bit like our type 1, what we talked about, null hypothesis testing, right? Because in essence, what we care about is, well, if I made a prediction, was that prediction correct? Okay. And so we could predict a true outcome, have true outcome. If we predict a true outcome, but it's actually negative, right? That's a type 1 error in the same way it is in null hypothesis testing. If we fail, or if we predict a false outcome and it's a true outcome, right? That's our type 2 error rate, and true negative. So this inner bit here is often referred to as a confusion matrix that I'll show in practice in a moment. And so we could sum these two cells here on the diagonal, and that's our model accuracy. There are a whole bunch of other things that you're going to learn over the course of this program in terms of prevalence, accuracy, right? So there's a whole bunch of other ways we can evaluate model fit. But for today, I'm just going to focus in on this inner square here. And the data set I want to just talk about quickly as our example, this comes from Kaggle. And what we're trying to do here is predict heart attacks from a whole bunch of variables. And so our outcome variable is this num. And if it's 0, essentially the patient didn't have a heart attack. If it's 1, they did. And there's a whole bunch of other variables here. And I have a link directly to the data set if you want to look at them. Oh, very quick, small digression. Because we don't really have time in this course to talk about missing data. I will point out, I'm not sure if I put this on, but I was encountering somebody. So this is just November 18th, a couple of weeks ago. A lot of people use mean imputation. So here's a little article I wrote up is to say, trying to explain to someone why I think mean imputation is worse than doing nothing. It boils down to you're kind of shrinking the variance. And the example I go through is if I had 20% missing, I do mean imputation, I may reject the null when I shouldn't reject the null. So I add data in at random. And if it's not random, you can have other problems. For your projects, I think we've said you can just remove missing data for now. But in practice, that is not what I would recommend. And so in the in this heart data set, there are 33 rows that have some missing data. And here I'm using the mice package because multiple imputation is so readily available in the R community, either through the mice package or there's another one called Amelia. I tend to have a preference towards mice. I find it a little bit easier to work with. This is all the code you need to do, and this will fill in the values in a way that preserves the variance estimations, so you won't screw things up. I will say this is not entirely correct. The recommendation is you do at least 5 missing full imputation sets. Here I'm just saying I'm doing one. There are multiple iterations, and you can actually change the iterations, but the default is 5. If you make m equals 5, which is the default, you will actually get 5 complete data sets. And depending on how you're doing it, there are some functions that will pull the variances across all the imputated data sets. What I tend to do is run my analysis with each of the 5. And if the results are close, I just pick the last one and move on. If I have a lot of missingness and there's a whole bunch of stuff, like I could do a whole lecture or 2 on missing data. To get the complete data set, I'm going to do this. So if you want to try this for your projects, I know presentations are this week, so it might be too late, but here's some code for you. Now, when I do this, I'm actually going to tackle this problem a little bit differently. I don't really care about just the relationship with just this data set. What I care about is making predictions to new patients, right, in this specific example. So in order to prevent overfitting, what I'm going to do is split my data set 70-30. So I'm going to use 70% of the data to train models, and I'm going to make predictions with the 30% that I hold out so that I don't potentially overfit. Now, if you're doing a lot of tweaking as you go through, there's k-fold validation and things like that you're going to learn later if you're doing a lot. But in terms of just overall model performance, this is a better approach. You can do better, but this is good enough for our work. The other thing I want to point out here is we need to be mindful of what our guessing or what our null model is. So here I'm looking at the training set and I'm doing a proportional table. And I see that in my data set, almost 70% of, I don't know why that number is wrong, but here it says 70% did not have a heart attack, right? And this is my baseline for comparison, right? Because here's the simplest model. I could predict no one has a heart attack, and I would be correct 70% of the time, okay? So that's what we're going to work for. So here I'm just going to use a logistic regression, pretty simple. And first thing I'm going to do is I'm going to look at the distribution of the predictive probabilities. A couple of things here to point out for those that are going to do logistic regression. If I have to, in the predict, I have to put type equals response. I can't remember if I showed that when we talked about logistic regression. This will give me predictive probabilities. Otherwise, I think it gives you the log odds by default, which is probably not what you want. So, and then I colored it by, treatment. So this to me looks generally pretty good, right? In terms of like those who didn't have a heart attack, I want the density to be more shifted to the left, because here, if what I'm going to do for now is say, well, if the prediction's greater than 50%, I'm going to say they're going to have a heart attack, and if it's less than 50%, I'm going to say they don't. So that's great. So if I think about, but the problem is like this blue line, which are those that did have a heart attack, there are quite a few patients that I would predict no heart attack. There's a handful of those who didn't that I would, right? So in this case, type 1 error might be worse than a type 2 error, right? I'd rather have a false positive than a false negative, right? So here I'm going to actually split. So I get predicted probabilities. I need to split at some probability to make it a 0, 1. And then here's my confusion matrix. So for 63% of the patients, I predicted no heart attack and they didn't have one. And 21%, I predicted a heart attack and they did. So if I add these two up, I get an overall accuracy of 85.37, which is almost over 15.5% better than the baseline or null model. So that's pretty good. Now, if we go back to that table with all of this, right, there's some other things. If I was a doctor, right, I might be a bit concerned about this 8.7% of people who I missed who did have a heart attack. Like, how can I make that better? And I might be like fine with this 5%. So depending on your goals, you may not just use the accuracy, you could use other things. However, I just showed you the accuracy using the training set, and I could potentially overfit. So really what I want to do is predict with the new data. So here I'm in the predict function, I'm giving it the test or the validation data set. Okay. So here I get 43.8 and 37, which gives me 80.9. So it's not as good as this one, which is expected, right? Because these data were withheld. They weren't in the model training. But it's still 30% better than guessing in terms of its baseline, which is a little bit different. this, I probably should have stratified this. Every semester, this is random. It's really random here. I didn't set a seed. And so I'm a little surprised I need to set a seed. So I don't, in this situation where my training validation sets aren't balanced the same, but I would have fixed that in a real analysis. Sorry about that. So last thing I want to talk about is receiver operator characteristic. So I've been cutting at 0.5, but that may not be the best. So I'm just going to go here. So what receiver operator characteristic curve is going to do is say, well, what if I split at 0.01, 0.02, 0.03? And it's going to calculate the false positive rate and the true positive rate against each other. And so if I have, like, if all my predictions are exactly 0 or 1, then my line would go straight up to here and straight across, right? And the area under the curve would be 1, and that would be a perfect model fit. But obviously, that's not what really happens. So in this example, with the heart attack, I do that, and I come across, and so this is my accuracy, and the area under the curve is 0.912, although I think that's a bogus, even though it's still reported everywhere. It's not really a meaningful measure in my view. It's not very robust, and it can be biased. But what's useful is on the right side, I have that accuracy curve. So essentially what happens is right here, right, this is the point where I have the greatest distance from the unit line. So anything that, if the line was exactly on the blue line, that would be no different than guessing. So over here on the right, it tells me, well, if I actually split at 0.657, that will maximize my accuracy. Now, 0.5 is not terrible. I bet you it's marginally different. So you have to make some, guidelines. And you could do a cost curve where you could weight the type 1, type 2 error rates differently. In this case, they're weighted the same, but in this case, we're looking for minimum values. Okay. Please, please be careful when you're predicting model accuracies because you want to go to that baseline. And the example I been pointing to for years now is this research that came out of Facebook. It was published in 2016, and this made a lot of news and freaked people out. They said with 90% accuracy using sport vector machines, logistic regression, or random forest, we could predict our users' sexual orientation. 90% accuracy. Wow. Facebook knows a lot by just what I click like on, right? Except when I was reading this paper around the same time, I was like, whoa, I just remember reading a Gallup poll that 4.5% of Americans identify as LGBTQ+. And I'm like, here's my model. I'm going to predict everybody's heterosexual. And I'm going to be correct 95.5% or 5.5% better than Facebook did with their gobs of data, right? So you really, really, really got to be careful, which leads me to this notion of, when you have imbalanced data, you're going to find your predictions are going to be hard. I'm going to gloss over this and go right to the picture. This actually came out of my dissertation work before predictive modeling was sort of the hot rage as it was, where I was trying to predict treatment or placement so I could do adjustments for selection bias. And in my case, I was doing a study with charter schools versus traditional public schools. In the United States, about 3% of students attend charter schools. So I have extremely imbalance. When I say imbalance, it means one class is much larger than the other. Okay. And so I'm using logistic regression to, estimate these probabilities of being in the treatment. And we're looking at diagnostic plot and noticing that, wow, the range of these fitted values is really constrained. And I had to figure this out. And so I wrote a little simulation just to kind of understand, to see what's going on. So what I've done here is I have, say, 100 treatment units. They're called treatment, so you can consider them the 0 class. And what I've done here is I have 100 of the 1 class. So I have perfect balance here, 1-to-1. And I have moderate separation. I simulated the data, and I'm running a logistic regression and getting the predicted probabilities. So this is the above is the density distribution for the 0 class. The bottom is the density distribution of the fitted values for the 1 class. I do this 20 times for each one. So this is the minimum of the fitted values. This is the maximum of the fitted values. And then I take the average of the maximum and the average, and that's what that is, right? So I'm trying to get a sense of what is the range of the fitted values from a logistic regression. And here I start with perfect balanced data equal 1 to 1. And I go all the way up until I have a 1 to 10 or an order of magnitude difference. So I have 10 times more I'm sorry, 0 classes is 1 classes. All else is being equal. This is all being sampled from the same data set that I set up front that has the same separation, has the same covariate sort of, coefficients. All else being equal, the range of the fitted values from logistic regression are going to shrink towards the majority class. So which is why I think when we go to things like this, I looked at this accuracy curve. So my split shouldn't be at 0.5, right? And the best I can tell is it's just an artifact of how logistic regression is estimated. Nothing we can do about it. It really screws up the interpretation of the fitted values in terms of predicted probabilities. But the logistic regressions can still be extremely useful. You just got to readjust how you do your cuts. This is where I'm going to end. So here's the 1-minute paper. But I will say if you want to download this slide deck later, and if you want to ask me questions, there's some of my slides on classification and regression trees. So you can go through that and ask me questions on Slack if you want to do it. But it's not going to be covered on the final, and you're gonna encounter it quite a lot in future class programs. But I just threw it in there if anybody wanted to look at it. Questions? Predictive modeling or Bayesian? This slide, Masood, can you clarify?
Yeah, that's that one.
So what do you mean by how would I wouldn't adjust coefficients. What I would adjust is I wouldn't cut if I cut at 0.5 here, then I wouldn't predict the 1 class for anybody. So what I would do is probably find some more. So actually what I would do is I would create this curve. I would create the ROC. And then what I would find is the threshold that would have the maximum accuracy is probably, somewhere over here. So instead of cutting at 0.5, I might cut it. And I guess in that case, it'd be like 0.125 or something. I don't know exactly. I'm kind of guessing by looking at the density distributions, but yeah. My point with this slide, be careful interpreting predicted probabilities from logistic regression. That should be my ultimate takeaway from this slide.
Right.
Yeah.
So would it help if we do like sampling from the data set, like, I don't know, 100-fold, and then do
you can do, a lot of people do, and I have done downsampling. And in the context of propensity score analysis, I have a package that will do just that for you, where we'll do downsampling across multiple data sets. So it's a kind of it's an approach that uses a little bit of bootstrapping principles and downsampling together, and then we'll pool the estimates across all the data sets. So it's called PSA boot. But it's really designed for propensity score analysis, which I will talk only briefly next week, just to talk about what like my stats research is. But you can look at this as sort of a way of thinking about that.
And last question, I'll let you go. Do you expect us to do any of these in our final project?
No,
Okay.
only if you're feeling brave.
Okay, cool. Thank you.
Well, there's always some students who will throw in a random forest or something just to try it. Because if you've done the logistic regression, doing any of these other things is going to be really not too difficult. In fact, if I scroll ahead somewhere in here.
I was just curious because I built
What's I'm
a
missing
lot
some
of
slides. Here, I'm just gonna show real quick. So here's random forest. So instead of GLM, I'm using random forest. My model structure is the same. Random forest has this weird thing that if if your dependent variable is not a factor, it may estimate a regression model and not a classification model. So you could do this little inline factor conversion and entries. And this importance is just so I can use something called random forest explainer. But yeah, so once you've got your your logistic regression set up, it's like it's really easy to get a random forest. So that's why I think some people like to try it just to see how it compares. Denise, I'm sorry I cut you off.
Just saying, I mean, I've done a lot of logistic regression models for predictive modeling and marketing and SaaS. And I know at one point in time I took a course at the SAS Institute. It was a statistics course, like, and it was just specifically in predictive modeling using logistic regression. And like they were saying, like if because I would typically sample down my zero events. I don't know what if I'm going to call that, but and and so and they had said in that class that if you do that, and I always still took into consideration like I looked at the p-values of each of the different parameter estimates, but they said to adjust the intercept afterwards because like at first take a stratified random sample where you're taking 100% of your your like LGBTQ population, whatever it is that's in like the minority and then and then you take a random sample of the other part. But then, and then before you do any kind of scoring, you have to adjust the intercepts to account for that, the fact that you oversampled, sort of. Am I making sense? I don't
Um,
know.
I'm not sure why the
Wait,
intercept would
yeah, that's what
be.
they had said. I mean, or they had a weighting that you could just weight it, like weight it, to account for the fact that because you mean you had a lot you like sampled 100% in a use a stratified sample, you sampled 100% of like if you were trying to predict, I don't know, who's gonna churn in a marketing,
Right.
situation, and then but you only took a random sample of the rest of it. I mean, honestly, part of the reason we did that was because it would run faster, but
Yeah.
um.
Yeah, and the model's not gonna, particularly logistic regression, maximum likelihood it's gonna have a hard time finding the separation when you have such imbalance. Some other methods will do better,
Yeah,
including
no, we would just
classification.
sample down the like
Yeah.
the not yeah,
Um,
a lot.
I'm not
Like
sure. I'll think about it, Denise. I have to write it. So in order to understand it, I have to run a little
I don't know because it was
simulation.
like yeah, because the guy that was I just remember because like they had a like I mean they came up with some strange stuff, but like because the guy that was teaching it, he was a PhD level statistician. He had a lot of experience like in the credit industry, and they've been using logistic regression I think in the credit industry for like forever.
Yeah. Yeah. I mean, it's been around for the generalized linear model has been around for a while. So
Yeah, and I mean, I've been like, that's been logistic regression,
yeah, I'll just find. Uh,
but I
I
didn't,
could find out pretty quickly if
I don't know how R handles it. Like, I just don't know because, like, I'm just saying that your predictive probabilities are accurate because that's
yeah,
we would
tidy
rank
models
things,
tidy
ranking
models
things by
will do some of
predictive
the adjustments
probabilities.
for you. So in this package, where do I don't know, that's not what I want.
Yeah, I don't know
So
because I did. I mean, I've done it in Python, but just like so I
yeah,
know
let me see,
how to.
did I write it in here? It might still be, or no, that's a balanced data set relatively. Yeah, I don't have it in here. Somewhere I have probably in my probably in my talk slides. Yeah, I'll do a little exploring. I'll find an imbalanced data set or simulate an imbalanced data set and see. I'm
It's
just
yeah.
curious. I I am.
'Cause like in Python, there were choices. Oh, like adjust for imbalance, but I had no idea what the hell that was doing.
Yeah, that's a problem. Tidy
I don't like that.
tidy models will do downsampling for you or upsampling if it's the other imbalance the other way.
Like they just said, oh, do this. Like, but I don't like it when you go like, well, why? So
Yeah, I'm just trying to figure out why the intercept would be different.
no, that was one way of doing it though, because there was another way of doing it in SAS, which was what I used because it was a lot easier to code. And I don't even exactly know how, but it was just using weights.
Yeah, and SAS is closed source, so I don't know how many people actually know.
Yeah, yeah, I don't know, because this was this one guy. I mean, because the adjusting, like I didn't understand that, and I think it would seem like very hard to code. And the other one because it was just kind of like much easier to do, so I just did the weighting because he said they weren't statistically equivalent, but resulted in similar,
Mhm.
results.
Hmm.
So I mean, because SAS, there was like 6 million ways of using the same procedure. I mean, because it's been around since like before I was born. So
Yeah.
it's just,
Yeah, I don't know. I don't know.
I don't know.
I'll
Yeah.
explore. Uh, any other questions?
There are two
Oh,
questions in the chat.
I'm sorry. What's the difference between linear regression and Bayesian model? Great
Mhm.
question. So high level. Well, we know the deep level. So linear regression is about minimizing the sum of squared residuals, right? We're trying to find coefficients, slopes, and an intercept that minimizes the sum of squared residuals. That is all predicated on the notion that the residuals are normally distributed, right? And that, right. So that's sort of how that's the frequentist approach, right? That this is going to be normally distributed because it's the central limit theorem. Bayesians are going to say, well, here's my data. I'm going to try to make a bunch of guesses on coefficients and see how well it matches the data I actually have. So it's going to simulate data to see how those coefficients, um, what the distributions, right? Now, it's not going to be single coefficients, right? It's all about probability. Like, so that's just going to generate these posterior distributions of all of the coefficients, all the slopes, based used by simulating data that looks as close to what you actually have. Okay. So very, very different way to think about it, right? Frequentists say we're oriented to the null. The central limit theorem says the sampling distribution is normally distributed with the standard deviation equal to the standard error, right? And we can make inferences. And if we theoretically could take an infinite number of random samples, and if our n goes to infinity, right? All the stuff we talked all semester, right? We're always orienting to the null. The Bayesians come in and say, you're crazy. We have all this research that suggests that the estimate should be near here. Why are we ignoring all the prior? Why are we going to the null? We know something. So let's see, based upon where we think it could be, right? Here's our distribution of where we think it could be. Let's estimate those parameters and see how much it matches what we actually saw. And that's what we're going to keep. We're going to sample from that and see how often it keeps. Our data, right? Bayesians will say data is truth, not some theoretical sampling distribution, right? That's how these debates go, right? Between Bayesians and frequentists. So uh so advantages and disadvantages. Um this is a great question. I don't know if I can answer because um they both have their place. And I sort of am a fair weather whatever. Generally, I will use both and use the one that performs better, gives me, what I want. Unfortunately, in the journals I read in terms of educational research, I rarely see people use Bayesian methods. So getting things published using those methods are less likely. But in the data science world where you guys are going, Bayesian's going to be used a lot, because
Um,
it generally performs better. So if you use um, the BART method, it's probably going to do better than logistic regression, to be honest, most of the time. Okay, now someone's asking, is random forest preferred over Bayesian? Um, in my experience, yeah, random forest actually still outperforms sort of the Bayesian regression models. Um, so again, when you get to uh 622 and 624, you'll look you basically a lot of times when predictions really matter, you you could train a dozen or more models and you're gonna, you'll learn better techniques than you'll have a validation and training set. But then within your training set, you may do k-fold validation. So there's some other techniques you want to use to prevent overfitting. But um, that's for another class. You'll try them all and you're gonna go, this is the one that works best for my data, right? And that's really, and things like the tidy models package makes it so easy to just keep swapping out or make comparisons across a lot of different methods.
Mm.
And I don't know if there's nothing. This is one thing where I know Python community, they don't have I don't think they have, there's some efforts to get something similar to the tidy models. But I don't think they quite have it. So really what Tidy Models tries to do is have a unified interface. So one of the issues is like the predict function, depending on the package. So if I have a logistic regression model, the default predictions are going to be log likelihoods, I think. Don't quote me on that. I have to check the documentation. The default value out of a random forest model for the predict function are predicted probabilities. So all right. So what tidy model says, when you call predict with tidy models, you're always going to get a predicted probability by default. And we'll figure out the details under the covers, right? So that's kind of one of it. Carrot was the predecessor, so that's still around.
I had one other question.
Sure.
Yeah, well, it's about so the lab that on multiple linear regression like that I finished but couldn't knit PDF,
Mhm.
because it said, like at the end, like, to remove, at least what I was, remove the variables who had parameter estimates that had p-values, above 0.05 because they're not significant. So even after you do that, and then it says to look at your residuals, and so after I did that and I looked at my residuals, I mean, I mean, I don't think in real life they're ever going to be perfectly normally distributed. I mean, it was less skewed, but it was still not.
Yeah. Yeah. I mean, that's again a whole other lecture on variable, how do you do variable selection? And if you go through the slides, a little bit on the classification regression trees and classification trees are a great way because they will only use the variables that are important. If the variable's not important, it won't show up. And so a lot of times you can use that as a way to inform your parametric models, your logistic regression models, and say, okay,
Yeah.
it's also a good way to
Hmm.
find interactions if you're unsure. Um,
Right. Well,
um,
I mean, it's like, I mean, it's just, yeah, like I said, I knew how to do something in SAS, but you can't do that. It was a proprietary algorithm. But, cases when you have like, like sometimes if someone you have 1,000 potential independent variables, like,
mhm.
then how do you figure out which ones to, you know?
Yeah, I have lots of thoughts, but I don't really want to go into it tonight. So we could talk at another time.
Okay,
Yeah, time's up. I'm sorry. Yeah. So if there are other
too too
questions, I'll
too too
stick around, but
complicated.
no one has to stick around at this point.
Yeah, right. I'm getting tired. I'll email both of you my lab because I couldn't figure out how to get it to knit to a PDF. I mean, because I just paste the error messages and then and sometimes it helps, but sometimes it doesn't.
Hmm. All right. Well, I'll take a look as soon as I can.
Yeah, yeah, because I don't know why I was just couldn't get it to knit. I finished, but I was just couldn't get it. Right. Thank you.
All right. Good night,
Okay, bye bye.
everyone.
Bye
All right.
bye.
Bye.